Jasmine asks to discuss number 7. Vincent asks to discuss number 6. Certainly. Um, so I'm going to give me, actually, I'll do them like this. I'm going to just get myself another page to write on. You all likely have access to the questions. If not, take a moment to dig them out. I have to do that myself. Homework. So questions 6 and 7 were the ones requested. Number 6 says a family is skating. The father collides and sticks to the mother, who was initially moving at some velocity. So the father, actually, I want to draw this a little bit lower on my page. So the father is skating this way. The mother is going at a 45-degree angle with respect to the father. And the two of them collide. They go off in some direction. And then they scoot into their child, who is stationary here. And then after that collision, all of them head off in some final velocity. So the question asks you essentially to find the final velocity of the all of them after they're done colliding. So this is just conservation of momentum. There are no external forces in any direction, right? I mean, vertically there are, but x and y, using this coordinate system, there are no external forces. And I know both of these initial velocities. So I know, whoops, I accidentally palmed my touchscreen. There we go. So I know the initial velocity of the father. Now that's confusing. I'm just going to use v father, v mother, and then here I'm going to represent this as v end, so we don't get confused by f being used for two different things. And since I know all of this, I know momentum is conserved in all of this. So I can just say that, oops, let me get my colors right. Here's the momentum of the father in the beginning. It's times v mother in the beginning equals, okay, so now what's going on in the end? So in the end, all of them are moving together, right? Mass of the child times the velocity at the end. Now what I've written down is a vector equation, but it's true independently and separately in x and y. So you can just write down x and y components of that, and this will work. Does this clear this up for you, Vincent, who's asking about number 6? Okay, good. Now let's talk about number 7. So number 7 was the pool ball question. I'm going to do this in full on and put it up on YouTube later today, as when I do the entire thing. So let's get a drawing of this. So I've got a cue ball. I may not get my arc quite right. So we've got a cue ball like this, and it collides with two other billiard balls, which I'm going to draw in blue. This drawing is going to look terrible. I apologize in advance. So here's one of them. Oh, that's awful. Even I can do better than that. So this thing is moving inward at some speed v naught. And then after the collision, all three of them go in different directions. So these two are going to go out. Oops. I know why I keep palming my touchscreen. Let me fix this. There we go. They're going to go out like this. We'll call these velocities, I'm just going to use v for them, for the final velocities of the balls. Since we might need to entertain the idea that they're different, I can represent them by v1. So one of the big tricks to this problem is recognizing that the centers of these three balls form an equilateral triangle, and in an equilateral triangle, all of the angles are 60 degrees. That means that this little angle here is 30 degrees. So that also means that the angles that these go off at are at 30 degrees, both of them. And given that, it's pretty easy to deduce that these two velocities are the same, because momentum is conserved in the y direction. So whatever upward momentum the top one carries, the bottom one must carry the same amount of downward momentum. So I'm not losing anything by using the same variable for both, right? I know those velocities are going to be the same. So now what I'm left with is conservation of momentum in the x direction. So I can write that v naught times the mass of a ball equals, so there's going to be some final velocity of the cue ball. The one on the left is the cue ball. And we don't know its direction. So this is the momentum in the beginning, because the only thing moving in the beginning is the cue ball. And in the end, I've got, this is the final velocity of cue ball. And then I've got the x components of the momenta of the other two balls. Actually, I'm going to write this one in orange just to keep my color coding consistent. So there are two of these. They're going at speed v, but they're going at 30-degree angles with respect to the horizontal. So this equation I have just written is conservation of momentum in the x direction. Because conservation of momentum in the y direction just tells me that the speed of the two balls is the same. And then I need to use, since I know this is an elastic collision, I know that the kinetic energy beforehand is the same as afterwards. So I can also write 1/2 mv naught equals, v naught squared equals 1/2 mvc squared, so the final kinetic energy of the cue ball, plus 2 times 1/2 mv squared. That's the final velocity of the other two balls. So here I've got a system of two equations in two variables. The two variables are v, the final velocity of the cue balls, or excuse me, the final velocity of the other two balls that were struck. That. and the final velocity of the cue ball. So I've got two things I need to solve for, and I have two equations, so I can in principle do that. And after that, it's just a matter of doing algebra. Any questions from anybody about that? So Jasmine, Martina, and Elliot asked about number 7. Does this clarify how to do this problem? Good, Martina. Any further questions about it? And I'll do the algebra on camera later. And that'll wind up on YouTube. All right. Yeah, Elliot, so about getting started. One of the things I have planned to practice later during this is I have some problems and we're just going to start them. We're just going to talk about what techniques to use. The getting started part here, you say, collision, conservation of momentum. Collision always means use conservation of momentum. This is an elastic collision, so you also know that energy is conserved. Let me write this down. By the way, everybody, I also post the PDF that I'm making here, like my notes with all of my drawings on them. That also is going to wind up online. So Samuel, in the y direction, if you treat their final velocities as opposite, in the y direction, wrong tool, you have that in y, there's no initial momentum in the y direction. You have basically m v1 sine 30 degrees minus m v2 sine 30 degrees. And this tells you that, that v1 and v2, I mean, if we put this plus sign here where we're thinking about this as, actually, I can't do that. Once I write sine 30, this has got to be a minus sign where v1 and v2 are referring to their y components. So I'm kind of thinking about this here where v1 is this one is the top one, v2 is the bottom one. That gives me this minus sign right here when I'm calculating the y component, and that just tells me v1 equals v2. So for this problem, in getting started, as Elliot says, we know that I should get off my highlighter tool. We know that this is a collision. So use conservation of momentum. And this is an elastic collision, which means kinetic energy is also conserved. So that's how you know how to get started here. Anything else about the homework? Pardon me while I slurp some water. All right, I'd like to spend a moment now